In today's video, we are going to use DeepMind's very own deep reinforcement learning framework, Acme, to code up a couple of simple reinforcement learning agents. Now, as you might imagine, Acme is an incredibly complex framework. As such, we are not going to have a whole lot of time to go over all of the intricacies of it today. Instead, in a couple future videos, I will look at how to create custom reinforcement learning agents using this framework. In particular, we're going to implement Soft Actor Critic and TD3, as these have not been implemented by the DeepMind team. Now, if you don't know anything about those two algorithms, never fear, I have a couple of videos linked over here in the top left. So the first thing we're going to want to do is copy the code from the GitHub. So we're going to copy the Git link and then head to the terminal and do a git clone. So we'll do that first. We will git clone, and that will clone into the Acme directory. And then we're going to want to create our very own virtual environment for this. Reason being, there are a number of dependencies for this, which will probably mess up your base Python installation if you should do this just willy-nilly without a virtual environment. So we'll do making our own virtual environment. We will then activate that. Of course, we have to cd into Acme and then do source bin activate, and then it will work. Then we have to upgrade our pip. And then we can begin the process of installing the DeepMind Acme framework. Now, keep in mind that being Google, this is implemented in TensorFlow, but they also have dependencies in code for the JAX library, which honestly, I don't know really anything about it. So we're just going to stick with the TensorFlow stuff. So we'll say pip install dmacme TensorFlow. And then we'll do pip install dmacme envs. This will give us some of the base environments. We will have to install Gym in a moment. I'll get to that in a few minutes. Now, Acme is built atop of many other packages written by DeepMind, one of which is something called Reverb. Now, Reverb is a framework for serving machine learning data, and the basic idea is that you have a server that serves data to any number of clients, and we're going to be adding data tables to this when we code our own custom agents. For the code we're running today, it's already implemented for us, but the basic idea is you create data tables within this server and then sample that data using whatever strategy you want, like say prioritize experience replay or end-step transitions, anything like that. Using any number of servers. It's highly scalable. It's an incredibly powerful technology, and everything we're going to be doing is built atop of that. And so then we also need something called Sonnet. Now, Sonnet sits atop of TensorFlow as a sort of additional framework for creating deep neural networks. I haven't played around a whole lot with it. I've used it for these projects, but it's not something I've done a deep dive on, and I don't really know what all is going on with it. So next we're going to want to install TensorFlow, and I'm going to specify a particular version. Reason being, the 2.8.0 release candidate has some conflicts with some of the other code, so I'm going to specify 2.7 because I know that works. Now, of course, if you're watching this in the future, maybe the 2.8 full release has no issues. Maybe they've ironed everything out. But for now, let's stick with what works. Next, we will need TensorFlow probability. Of course, this handles probability distributions for policies. Next, we need to install something called checks. I don't know what that is, honestly. I didn't have the energy to look it up. Next, we have TRFL, Truffle. That is a TensorFlow reinforcement learning agent package. And then we want to do an upgrade for Gym Atari, and it's really a downgrade because we're running 0.21. We want to downgrade to 0.19 because as of 0.21 or perhaps 0.20, they quit including the ROMs with the Gym environment. So when we try to run Pong or any other Atari game, we're going to get an error. So let's downgrade to 0.19, so we should be good to go. So now we can do a list, go to the examples, we can go to Atari, and then we can see we have a whole bunch of files here. We have run DQN, run Impala, and run R2D2. We're just going to run a DQN here to make sure it works, and I'm expecting this error here. So now this is easy to deal with. What it's telling us is that we don't have a particular shared object file. So of course I am running Linux Kubuntu 20 if you're curious. And so I haven't set up the LD library path environment variable in this particular virtual environment. So we can check that by saying echo LD library library path, and I believe I need the $ here because that's a variable, and it tells us it points to CUDA 10-10.1. So then we can locate that particular file to see where it lives and why it's unhappy. So we'll just do libpython 3.7, and we can see that it lives in this particular directory. So what we're going to do is export LD library path equals that directory $LD library path. And so let me move my face out of the way here. The $LD library path will with the $ will append the current variable for the LD library path, and we can verify that by echoing it to the terminal, and we see right here that it now includes both directories as we want it to do. Now if you're running Windows, I don't know the fix for this. I don't use Windows except for some light gaming every now and again. You should probably upgrade to a real operating system, preferably Linux, although probably Mac is going to be up more people's alley, but nonetheless, let's try running this again. Okay, so now it is starting the reverb replay server, saving some checkpoints, and I can see it spooling up my CPU usage now, so that tells me it is running. Okay, so we do get some output to the terminal. You can't see it, but it's telling us table priority tables access without gRPC. It's not doing any calls over the internet because it's just my local machine. It has some code that indicates it is learning by outputting to the terminal, and then it also does some output from each individual episode, telling you the return, the length, and all that good stuff. So let's stop that code. It takes a second to shut down the replay server, and then we're going to code up our own DQN agent as well as our own DDPG agent to see really how easy it is to get started with this. So we're going to get out of this directory, and we're going to go back here just to the base Acme directory, just for giggles. So we're going to vim into dqn.py, and we're going to start with our imports. We're going to say from absol import app. We're going to use app.run to run our program. Let me zoom in a little bit for you guys. And then we're going to import functools. You'll see why we need that in a little bit. Now all of our environments are going to be wrapped. If you've taken my course on deep Q learning, you probably understand that. It just means that we're going to take the output from the gym environments and then apply operations like, say, converting the screen images from integers to floats by dividing by 255, and we're going to stack frames and repeat actions, that kind of stuff. So acme.agents.tf import DQN, so we're going to import the actual agent, and from TensorFlow we're going to import the networks. Now, as I said, sorry, I can't talk and type at the same time. As I said, we're going to be using all of the building blocks they give us, and so the structure of their program is a little bit different than what I typically code on this channel because they are professionals and they know best. Their structure is that they have an agent that has both an actor and a learner. So the actor is basically the policy, and the learner basically collects the data from the reverb data table and uses that to update the deep neural networks. And those networks are defined in that package networks. sub-package networks. And so we are going to be assembling all these building blocks into a deep Q learning agent that we're going to test. So the first thing we want is a function to really wrap all of our environments. And this is written, all of our code is written using, I guess this type of syntax of specifying the typing came about in like 3.7 or maybe 3.6, something like that, which I really like. It is one of my biggest complaints about Python is that it's not a strongly typed language. Now, of course, this doesn't make it strongly typed, but it goes a long way towards rectifying that issue. So here we're going to specify our level, no frame skip -v4, and they have something called an OAR wrapper. What that does is it takes the time step from the environment and wraps it into an observation action reward tuple. They use it for some of their agents, but not for the deep Q learning agent. It's a little bit, I find it a little bit inconvenient. Obviously, they do it because they find it convenient. But for someone from the outside looking in, it's a little bit difficult to wrap your mind around. Maybe I'm just a moron. I don't know. Other thing to note is this arrow and then the return type. That tells the Python interpreter what to expect for a return type. Now, as far as the typing, what I'm talking about specifically as a brief aside is that in Python, you can pass in a variable to a function and change its data type from, say, a float to a string or from a custom object to a Boolean. And Python never says, hey, did you really mean to do that? And it can result in some subtle bugs down the line if you write your code in such a way that it's not strongly dependent on a particular data type. So sometimes strings will evaluate in certain ways versus floats, and it can make it inconvenient to track down bugs. So I'm glad they at least inserted some features to at least improve the type checking capabilities. So we want to make our environment level full action space equals true. I believe what that means is that in the ALE imports, the ALE environments themselves, you have a total of 18 actions for all the Atari games, whereas in some of the OpenAI implementations, they reduce it down to just the stuff that actually does something. So you don't have like 16 no ops and then 2 actions that actually do anything. So then we'll say max episode length equals 108,000 if evaluation else 50,000. And then we're going to make a wrapper list that just tells the module what we want to do. So we'll say wrappers.gym Atari wrapper. That is going to handle all the good stuff like stacking frames, converting to grayscale, resizing. And then functools.partial. This will apply the Atari wrapper. And toFloat equals true. That means we're going to convert the observations to a floating point number instead of integers. And this 0 discount on life loss, I believe what that means is it sets the reward to 0, the total discount to 0 at the end of the episode. So that the loss of life actually affects the agent. That's my understanding. Again, I haven't mastered everything within this framework, so take that in mind. If you are a little bit more familiar with it and I say something incorrect, please correct me in the comments. I don't claim to be an expert on something that DeepMind wrote. I'm just using it to learn how the experts do stuff. So then we're going to wrap all of our wrappers into our environment and return it. And then we have our main function. And that's not a typo. You do need that underscore there. And we're going to say env equals make environment. We're going to need an env spec. Sorry, what that does is it gives us the specifications for environment, like the shape of the observations and action space. Make environment spec. I'm going to pass in the environment. Now here we're going to kind of cheat a little bit and use their built-in networks. So they have one specifically for a DQN in Atari. ENV spec actions.num value, so we have to specify the number of actions. Now what this does is that it creates a it'll create a convolutional network, just like what we see in the DeepQ learning paper, where it's got a bunch of convolutions, and then we'll actually implement the dueling architecture from the paper on dueling architectures for you, so you don't even have to worry about that. And then our agent, we're going to need to pass in an ENV spec and a network, and then we need an environment loop to play the game. Environment loop ENV agent, and then we're going to run. We're just going to do 10 episodes. Other thing I want to note here is that the default parameters don't give you good learning, so you do have to do hyperparameter tuning on this. That's one way in which, you know, they don't completely and totally hold your hand. And so then we want to run our app. Now let's, it's unhappy, expected 2 lines. I upgraded my Vim installation with some PEP 8 guidelines, and it's unhappy about something else. Undefined name bools, that's because it is bool. There we go, and now it should be okay. So let's Python dqn.py and see what happens. Module Acme wrappers has no attribute Jim Atari wrapper. That's because it is Jim Atari adapter. That's right. There we go. That is a typo. Let's try that. Okay, so it's loading our reverb server. That's a good sign. And then boom, it is learning. So you see how incredibly easy it is to get this up and running. But we didn't really do a whole lot, so perhaps it's not all that satisfying for you. In particular, one thing we can do to have a little bit more involvement in the process is to actually define our own networks. And so to demonstrate how to do that, I'm going to show you how to do a DDPG agent, which of course has the policy and critic network, the actor and critic network. So let's terminate that. Okay, and then we're going to do deep deterministic policy gradients. So we'll say from absol import app. We'll need our wrappers again. And again, they have a DDPG agent, which takes the networks, handles the interface to reverb, handles the functionality to actually add memories to that server, the data table on the server, has functionality for sampling a TensorFlow data set, as well as functionality for handling the learning. So there's a lot that goes on under the hood in these agents. And again, I'll come back later to do soft after critic and twin delayed deep deterministic policy gradients, but we're kind of running along already, about 20 minutes, and so I just want to give you guys a brief overview of how all this works. So we say from acme.tf import networks. We're going to need some utilities. We'll need Acme, Jim, NumPy, Sonnet. They always abbreviate that as SNT. And we will need TensorFlow. Next, we have our main function. We're going to make our environment. I have a few different possibilities here. I'm going to use the pendulum v1. That is just a swing up pendulum. It's a very simple environment. But this is not in a format that DeepMind's framework is going to expect, so we have to do a gym wrapper to handle the interface with the DM underscore environment, the DeepMind environments. And one common thing they do is use the single precision wrapper to convert everything to single precision to get max throughput on your GPU. Then we make our environment spec. We're going to need the number of DIMMs in our action space. So we'll say mp prod env spec actions shape and cast it as an int. Batch concat. Then we have our policy network sonnet sequential. This is where sonnet comes in. So we're going to pass it a set of layers. So we'll say layer norm MLP multi-layer perceptron. We'll do 64 by 64 by n DIMMs. And what this does in simple terms is it makes 3 layers of shape 64, 64, and n DIMMs of a layer norm linear layer, basically. So what essentially they implement in the original DDPG paper, and the final activation will be a tan hyperbolic. Very, very simple, very, very elegant. We don't have to handle compiling or anything like that. That gets handled by Sonnet under the hood. Critic network, another sequential network. We'll have what's called a critic multiplexer. And what this does is that it concatenates the observations and actions as we do in the original paper. Then we have another layer norm, MLP, 64, 64, and 1. Of course, 1 because this is the critic network. It outputs a single value. Next, we have our agent. It's a DDPG agent. We have to pass in a little bit more this time. I call it env spec up here. I did env spec. And then we have our policy network, our critic network, our observation network. I'm not entirely sure what this is. Again, I haven't dug into everything yet. I'm just kind of excited about this and showing it to you guys as I go along. And then whether or not we want to checkpoint our agent's learning, we'll set that to false because we don't really care at this point. Then we need our env loop again. Acme environment loop. Pass in our environment and our agent. And run for just say 10 episodes. And then app.run main. All right. So yeah, it expects more spaces there, and that was my only error. So let's go ahead and run this and see if I made any typos. DDPG. Pendulum 1 not found. That's funny. I must have different versions in my different directories for this. Obviously, I've done this before. So in the other one, it didn't find pendulum v0. So let's switch that out to v0 and try again. And there we go. It is running already. So you can see how incredibly easy that is. They do have one warning here. This looks like they put gradient tape.gradient inside of a loop or something. I didn't do that. Let me scroll down so you can see that. That's something in their own code. I'll probably take a look at that when I write the TD3 agent because it'll be relevant to the project. But yeah, otherwise, you can see how incredibly simple it is to run this. And it did 10 iterations very, very quickly. So that is how you code agents like DeepMind. Now, obviously, some things that stick out to me are that, one, there is a lot of complexity there because deep reinforcement learning at the scale they do it is incredibly complex. Another thing that sticks out is that there as far as I've seen, and I could be wrong, but as far as I've seen, there's no simple way of running agents in parallel. So with something like R2D2, which is a recurrent distributed DQN agent, they run in the paper 256 actors in parallel. And the agent they supply here is a single-threaded version. There's no multi-threaded framework to stick on top of it. Now, of course, you're free to do stuff like Python multi-threaded stuff, or maybe even MPI type stuff on top of it. But it would be helpful to see how they do that. But of course, they want to keep their secret sauce to themselves. They can't, give everything to the world because they need a competitive advantage, right? They need to keep some cards close to their chest, which I totally and completely understand. Other thing is that their hyperparameters are not tuned, so I played around a little bit with these two agents and couldn't get very good learning. And so that probably means I need to tune hyperparameters, but for the purpose of this video, I didn't get too excited about that. So that's something to keep in mind, is that even if you do use this, it's not totally off the shelf. You do have to do a little bit of tuning, but they've done 90% of the work already. So what more do you really want, right? Okay, I hope that was helpful for you guys. This is an enormously interesting framework for me. I've been digging into it, trying to implement something called Never Give Up, which is a highly complex algorithm. And so I found this enormously useful. It's something I wanted to share with you guys, something I'm going to dig deeper into in the coming weeks and months. And I hope you will join me for those videos. Go ahead and give a subscribe if you haven't already. Drop any questions down below, and I'll see you in the next video.